Okay, left. Okay. Okay. Fine. So I was telling first we will discuss the turn-on mechanism or the SCR triggering methods of an SCR. So after the discussion what we have, at the end of the session, I will call few of you. You will be describing or explaining the turn-on switching characteristics of an SCR. Okay. So just give me a moment. I would like to open the student list. Just a moment. I'm trying to open my student list so that I can call you randomly. This is not student list. Okay. So when I call your name randomly, you should be able to respond to me and explain the questions. I mean, answer the questions. All right. So which means that you are supposed to be attentive. Okay. So moving on. So I said in this session we are discussing turn-on mechanism or also called SCR triggering. Okay. So what is triggering? The triggering is nothing but the process where you turn on the SCR. Okay. So in a simple words to say, if you are switching the SCR from forward blocking mode to forward conduction mode, that is nothing but triggering. Okay. And to do that, that is to turn on SCR, we have these following different methods. So first is forward voltage triggering. A few of them, like you have already discussed, you are already familiar about that, forward voltage triggering. And second is thermal or temperature triggering, radiation or light triggering, then dV by dt triggering, and finally the gate triggering. So you are already familiar with all these. Okay, you know what they are. We are just relating that to how we can turn on the SCRs. All right. So first, forward voltage triggering, we are already familiar, where we apply the voltage across anode and cathode, right? So we know that when we apply voltage across anode and cathode terminals, the junction J1 and J3 will be forward biased and junction J2 is reverse biased, right? So in that condition, because of the depletion region, we know that J2 blocks the current or there is no current flow. Unless, I mean, there is some small amount of current due to minority carriers, that we call it as leakage current, right? So we know that as we increase this VAK, the voltage that we apply across anode and cathode terminals, so there reaches a point where there is a breakdown of junction J2 taking place. So that voltage, we call it as forward breakover voltage, right? So that is where the device turns on. So when the device turns on means immediately the current starts increasing. This anode current, what we say, it starts increasing tremendously, and voltage across the device will be minimum, right? So we know that when the device is turned on, okay, the voltage across it will be very less. So in terms of SCR, it is 1 to 1.5 volts, okay? So we know that for diode, a simple PN junction, it is 0.7 for silicon type, right? And 0.3 for germanium type. So if for SCR, you need to remember the voltage across it when it is turned on will be typically around 1 to 1.5 volts, right? So some points to remember here, which we are already familiar, just to say underline the things, okay? So when breakover voltage crosses a specified amount, okay, then that is the supply voltage. If it reaches breakover voltage or more than that, then the SCR turns on, right? And the moment when the SCR turns on, the anode current, what we get there, that will be our latching current, right? So according to our definition, if you recall, what is our latching current? It is the minimum current required to keep the SCR in turn on condition. Okay. So when the device is turned on, when we increase this forward voltage, that is voltage that we apply across anode and cathode, the moment it is turned on, the immediate current what we measure, the anode current, is our latching current. Because what, if you recall the construction and working, that is the minimum current that will drive the SCR to start conducting, right? So recall the construction and internal structure there. Remember the back-to-back connection of two transistors, okay? So if there are minimum charges which are driving the, say one transistor, so that will be in turn, which is connected to the base of the second transistor, which will be as a base current, which will trigger the next transistor, right, to turn on. So eventually there is a continuous flow of current. So this minimum current is nothing but our latching current, all right? So then generally in power electronic circuits, usually this breakover voltage method, that is forward voltage triggering method, is not recommended, or it is not suitable to turn on the device. That's why most of the circuits will try to avoid such condition. As we know that from our previous session, that manufacturer will provide all these values, that is what is the breakover voltage, what is the minimum voltage to trigger the SCR, what is the maximum range that can be applied, all those things. So during applications, one should look at the data sheet of particular device what you are using, particular SCR, and your circuit should be in such a way that it will not unnecessarily turn on the device. So care should be taken in such conditions, okay? So here it says that when a thyristor is triggered by exceeding VBO, that is forward voltage triggering method, the fall time of the forward voltage is quite low, which means that the switching of the SCR is faster here, okay? So it says about 1/10 of the time taken by the thyristor in gate triggering, all right? So it means here SCR will turn on or say turn off faster in this method, okay? So if you look at the last point there, so turn on time for this forward voltage triggering type, this turn on time is lower. So turn on time is lower means obviously switching is faster, right? So next is thermal or temperature triggering. So here we know that the width of the depletion layer of SCR decreases with increasing the junction temperature. So how do you say that? We are aware that the conductivity of a material is determined by two factors, right? One is the concentration of the free carriers available to conduct current and their mobility. What do you mean by mobility? It is nothing but freedom to move, right? So in semiconductor, both mobility and carrier concentration are depending on the temperature, okay? So that means as you increase temperature, the conductivity will increase, because in turn what is happening there, the mobility of the charge carriers increase, so which in turn will be increasing the conduction. So therefore when SCR is subjected to say VAK around or near to breakdown voltage. So the device can be turned on by increasing the junction temperature. Okay. So increasing the junction temperature, what happens? The reverse bias junction, that is J2 junction, will collapse and the device starts to conduct. Okay. So next is our radiation type or the light triggering type. So as the name indicates, you can turn on the SCR by applying light or applying some radiation. Okay. So observe here. So instead of gate, there is a niche. Okay. There is some a point where instead of gate terminal, this niche is placed wherein if light is applied there, if the radiations are made to fall on this area, okay, so that can turn on the device. So what happens when the light is allowed to strike this terminal? Free charge carriers are generated here in the P region, all right? And when the intensity of the light becomes more, then the thyristor will be turning on. So such type of thyristor or the SCR is called LA SCR or light activated SCR. Okay. I hope you're noting down all points, and please stop me if you're feeling that I'm fast. All right. Please stop me whenever you feel I'm fast. And I hope you're noting down points. So at the end, you may expect question at any point and to anyone. All right. Fine. So in light triggering, what happens? Some points to ponder here. So in this method, light particles, that is photons, are made to strike the reverse bias junction. Which is the reverse bias junction here? The J2, right? So which causes, that is light particle will cause an increase in the number of electron hole pairs and it will trigger the thyristor. So when it is irradiated, what do you mean by irradiation? Irradiated means what? Or irradiation? It is nothing but the process of applying radiation, right? So the free charge carriers are generated similar to the way what we were discussing in the gate signal, gate control signal. Okay. So this pulse light, if with appropriate wavelength, if appropriate wavelength is applied, then as the intensity of this light increases, then the junction J2 breaks down because of the more number of electron pore pairs that is generated there, so which will cause the SCR to turn on. Okay, so mainly this type, that is LA SCRs, are used in high voltage direct current transmission systems. The application lies here. Right. The next triggering method is dV by dt. Okay. So what do we understand with this dV by dt? Say, if you recall, you have junction J1, J2 and J3. You have applied voltage across anode and cathode. Okay. When you are applying voltage across anode and cathode, junction J1 and J3 are forward bias. Junction J2 is reverse bias, right? So here what happens, there is a depletion layer getting formed, right? So the charge carriers that are getting deposited here in junction J2, if you recall the depletion region and the width of the depletion region and all those things, and how the charge carriers or the immobile ions where they get accumulated across the junction, if you recall all those points, then this junction J2, it behaves as a capacitor because there is a deposition of charge carriers at this junction J2, right? Now, if you apply the information about capacitor here, that is because of the charge carriers, if the voltage across this, okay, if we say the charge is represented by Q and the voltage is represented by V, then the capacitance, that is across this junction J2, if you are taking it as a capacitor, then the capacitance C, it is given by IC, Yeah, the current, capacitor current, or the current because of the capacitance. It is given by, you know the relation here, it is nothing but dq by dt, where q is your charge carriers, right? So the Q is given by C into V, where C is the voltage, what you can imagine across it, and C is the capacitance. Okay, so applying that relation here in the collector current, all right, IC is equal to D times, in terms of Q, you apply C and V by dt. Okay, this collector current is nothing but rate of change of charges with respect to time, right? So we are just substituting Q here. So if you substitute, split it, what you are getting is C into dV by dt plus V into dC by dt. Simple differentiation, what you know about that. So since you know that capacitance, you can say there is no change with respect to time. So this term goes to 0. So if you equate that, then the IC, they say the current flowing across this junction J2 can be given by C into dV by dt, which means what? Where the current that can flow through this, it mainly depends on the voltage that is varying. All right, so the rate of change of voltage with respect to time is what controlling the current. Okay, I hope you're understanding that. Okay, so which means that if you have to increase the current flowing through this junction J2, then it is mainly depending on the rate of change of voltage. Okay, as you increase the voltage, obviously you can imagine high current to flow through this. That's a meaning. Okay, so generally, again, most of the applications will see that this dV by dt is under specified limits. All right. So that is what here the last point says. When the rate of change of voltage across the device becomes large, the device may turn on. So here the point is about the junction J2. So if even if the voltage across the device is small, that means what the voltage what you are applying across anode and cathode. So even this voltage VAK is small, but here if you are increasing the rate of change of voltage across this, even that can trigger the device on. So how do we do that actually? It's nothing but something about the gate terminal, right? So that is the final gate triggering. All right, let me see who is attending here.
Hello, ma'am.
Yes, somebody speaking. Yes.
Ma'am, I had a question in the last slide, dV by dt triggering.
Okay. Who is this? I am not able to make out.
Sagar, ma'am, Sagar.
Sagar. Sagar, please tell me.
Ma'am, can you go to the previous slide, ma'am?
Sure, sure, sure. Okay. Yeah.
Ma'am, there it is, when we consider IC equation, it is given as a differentiation of CV, and
Hmm.
dC by dt is taken as 0, where C is capacitance, which we know expression is epsilon naught A by D. So D becomes the width of the region there, the
Yep.
near that gate region. So
Yes.
and we know that width will change with when we apply the voltage. So in the previous expression, I see we are considering that dV by dt is present. That means voltage is varying. And if
Hmm.
it is varying, then capacitance will also vary, right? So because the width is varying. So why dC by dt is 0 then if dC is varying?
See here, in term, okay, okay, let me just think over that. Uh, okay, your point was why dC by dt is equated to 0, right?
Yes, ma'am. Because capacitance will depend on width. It is inversely proportional. Width of the junction, and width of the junction will vary with respect to voltage applied. So then it shouldn't be a constant. So it should vary. If that expression is partial derivative, then we can take it as 0 dc by dt.
Okay, yeah, I got your point actually. I got your point. Like as we say apply voltage across gate terminal, obviously the width will decrease, which means that this DC by DT term also will be varying, right? That is what
Yes,
you're
ma'am. It is
saying. Yeah,
finite.
yeah, yeah. Yeah. Okay, let me. No, actually, what I feel here is, yeah, it is actually partial differentiation, right? Um, uh, yes, can anyone think over that? Can anyone suggest why is it equated to 0? Why is it equated to 0? Anybody can you think over it? Actually, it is like the rate, it is not exactly 0. The rate of change of this capacitance, what is taken, it is taken as negligible. That's why it is equated to 0. Okay, it is,
Okay.
see, yeah, it's not exactly 0, but it is very small. The rate at which it is changing, the what is that, width of the depletion region. So if you take in that terms, the rate at which it is changing, the capacitance is changing is negligible, then it is saying you're taking it as 0 and you're substituting IC is equal to C into dV by dt. Got it?
Okay, ma'am. So there is no much large change in width of the depletion when we change voltage.
That's what. That is what the meaning. Like the rate at which it is changing is negligible. That is the meaning.
Okay, okay, ma'am. Because
Okay.
capacitance is inversely proportional to width. So even if there is a small change, that might lead to a big difference in the C value.
Yeah,
So
yeah. That's why it's taken as negligible.
okay,
Correct.
so
Correct.
okay, ma'am. Okay,
Yeah.
okay. Thank you, ma'am.
Yeah. Does that convince you?
Yes, ma'am. Yes.
Yeah. Thank you, Sagar. Yeah. Thank you for this discussion. All right. Shall we proceed? Okay. Okay. Yeah, we were here. All right. I just pondered here, like I wanted to know how many of you are alert. Let me ask question, somebody to explain this. Matthew Babu, can you come in?
Yes, ma'am.
Yeah. Can you explain gate triggering? What do you mean by gate triggering? Where we have already discussed
Uh,
about that. Yeah.
yeah, ma'am. So basically, the gate voltage and current.
Mm.
So it will vary where the switch of the SCR will come on with the reference of the gate voltage and current.
Okay, so tell me those conditions, like what are the conditions? What is that? What signal is given at the gate terminal? How is it making any difference? What about the junction conditions? What about the voltage you are applying to the device? All such information should come.
Okay, ma'am. Actually, talking with respect to the characteristics, ma'am.
No, no, no. Like we have already discussed about turning on SCR using gate control signal, right? So if
Yes,
I
ma'am.
want you to relate that, like what is gate triggering? What do you understand? Gate triggering means what? Is my question. Okay, you have given me some points. Let me go to someone else. Okay, Royson D'Souza, can you come in? Royson D'Souza.
Yes, ma'am.
Yes. Can you tell me anything about gate triggering? What strikes your mind? What is gate triggering?
applying positive signal to the gate.
Okay, that's what Matthew also said just now. Like, give me the conditions, right? What are the other scenario there if you are giving some voltage to gate terminal? What about other things?
Uh,
I just mentioned what is the voltage you are applying across anode and cathode, what is the condition of junctions, and what happens with that signal, what you're applying to gate terminal. All those information should come. See, when we just look at, we feel we know things, but when exactly we have to put it across, that is where we will stumble. Not getting any idea there? Can I go to Saichit? Saichit, can you come in? Saichit.
Good morning.
Good morning. Yeah, tell me, Saichit, can you explain what gate triggering means?
The same thing.
Same thing. Same thing means what? Put that in terms. Same thing means what? Put it in the
Ma'am,
terms. Yeah.
turning on the thyristor by the gate triggering.
Turning on the thyristor by gate triggering. Okay. Fine. We'll proceed. Okay. Pay attention. At the end, I'll come back to you. You have to explain the next points. So, turning on of thyristors by gate triggering is simply what we have already discussed, that we are applying voltage to the gate terminal, right? So, what happens here, even if the breakover voltage or the supply voltage, what you are applying it across anode and cathode, if it is even below breakover voltage, then if you recall the characteristics, by applying control signal or the gate signal, okay, you can make the thyristor turn on, or you can make the SCR turn on from blocking state to on state. I hope you recall the characteristics there. So even the voltage applied across anode and cathode, even if it is below VBO, that is breakover voltage, you can make the SCR turn on faster or quicker or sooner by applying gate signal. Recall that? Yeah. So what we do then? We apply a gate voltage, that is we apply some voltage across gate and cathode terminal, because of which there will be a current flowing to gate terminal, right? So that will inject or initiate the charge carriers to increase in this junction, and that will be making this junction J2 break down, which will cause the device to turn on, right? So that is what is explained in all these points here, just now what I mentioned. Whenever thyristor turn on is required, a positive gate voltage between gate and cathode is applied. So with gate current established, charges are injected into the P layer, and voltage at which the breakover occurs is reduced. Okay, the same thing what I explained in a more professional way, that's all. Then to have more information, just to, yeah, so yes, so that's what I was just saying. This PN junction, because of the increase in the charge carriers and as it behaves like a simple diode, so there is a conduction taking place which will allow the junction J2 to break down, and that will trigger the SCR on. Okay, so here the points what we have to recall, ponder or underline is, you can turn on the device even at the supply voltage is below the breakover voltage. Remember in the last session, in the recorded session, I had explained that. Okay, where we had one example and we were discussing few points there. What happens if the breakover voltage is this much? What happens with a triggering current is this much? If a triggering current is increased, then what happens? So all these points is what is summarized here. Okay, so it's nothing but these are the different ways you can turn on the SCR, right? Now, we will stop or pause here just to have a break. Break in the sense, I want you to tell me or give me the answers for this problem, example problem, what we had in the last session, previous session. Let me ask someone the answer for this. Okay. Kshama Shetty Kshama. Can you come in? Kshama? Okay, she's not there. So I have to note down. I have to note down the names who are not responding to my call, which means you have just logged in and you have vanished. Okay, Shushma K. Rai, are you there? You are not there. Good.
Hello, ma'am.
Yes, Shushma, you're there.
Yes, ma'am.
Okay. You have the answers for this problem? Have you gone through this problem? Yes or no? I'm expecting some answer here. Have you gone through this
No,
problem?
ma'am.
Huh?
No, ma'am.
No.
No.
No. Okay. That means I have to note down that you have not gone through the session, right? Tripti, can you come in? Tripti? Tripti, are you there? Not responding, so you're not there.
Hello,
Okay.
ma'am.
Yes, Tripti is there. Have you gone through this problem? Can you give me the answers for this?
No, ma'am.
Okay, yes. All right. Velen Pinto, can you come in?
Yes, ma'am.
Yeah. Have you gone through this problem? Do you have
Yes,
answers?
ma'am.
You have answers?
Yes, ma'am.
Okay, very good. Thank you. I'll come back to you
Yes,
a
ma'am.
bit later. Yeah. Princita? Princita,
Yes, ma'am.
you have the answers?
I know.
Yes or no?
No, ma'am.
Okay, fine, fine. That means you have not gone through the session, is it? The recording session?
I have gone through the session, ma'am, but I didn't solve this problem.
You didn't try the problem. Okay. Yeah. I appreciate if you are very frank and honest. I appreciate that.
Yes.
Okay. Yeah. Let me check few more. Lohit, Mr. Lohit, can
Yes,
you come
ma'am.
in? Yeah, are you there? Okay. Have you got the answers for this problem?
No, ma'am. The last problem I didn't try.
Try. Very good. Kavyashree, can you come in? Kavyashree. Fine. Not responding. Good. So, okay. Then let me, others please bear with me. You know what I'm trying to do here. Okay, Navya Ramachandra Nayak.
Hello.
Yeah, you're there. Okay. Catherine? Catherine?
Yes, ma'am.
Okay, you're there. Have you tried?
Yes, ma'am.
You've tried. Can you give me the answer?
RS is 14 ohms.
RS. Okay. Yeah, good. Very good. Yeah, thank you.
PV.
It's okay. Enough.
Thank you, ma'am.
Yeah, thank you. Sohan, PV Sohan.
Yes, ma'am.
Yes. Have you tried the problem?
No, ma'am.
No. Okay. Yeah. I appreciate that frank answer. Thank you. All right. Okay. Please don't mind. It's not like I'm patrolling or policing you. It is just to make you realize your responsibility. That's all. Okay. You have to be behaving as a responsible grown-ups. It's not like just you log in and just vanish off. Yeah. When we are doing our work sincerely, it is your part to be attentively attend all the live sessions. All right. Okay, fine. So I had given hints for this problem in the previous session. Here is the solution. You can note down. Please note down. We will discuss here. Yeah, according to the question, see, for an SCR, the gate cathode characteristic is given by the straight line with the gradient. Gradient is given here, 16 volts per ampere, okay, passing through the origin. The maximum turn on time is given as 4 microseconds. Maximum turn on time is given. And minimum gate current required to obtain this quick turn on is 500 milliamps. So minimum gate current means IG is given. IG is given. If gate source voltage is 15 volts, gate source voltage, if you recall the circuit, what we have there, it is ES, right? So ES is given as 15 volts. Then what is asked? Calculate the resistance to be connected in series with the SCR. So if you recall the circuit again, the RS, resistance RS that was connected in series with the gate terminal, that value is asked here. Calculate RS. So to do that, I had told in the previous session, I had given the hint that if you apply Kirchhoff voltage law to this loop, okay, what you get is ES is equal to VG plus IG RS, right? Okay, so in that expression, ES you know, IG you know, all right, you don't know VG and RS, okay. In the first subsection, subquestion, RS is asked, but you don't know VG as well here. So VG can be found out by the gradient that is given there. Gradient is given. What is gradient? Can anyone tell me what is gradient? So in gradient in a power system is nothing but it is defined as the rate of change of the electrical parameter or the potential, okay, with respect to the distance. So rate of change of electrical potential means what? It is voltage in the numerator. All right. With respect to distance means what? It is nothing but the current. So here we are talking about the variation of voltage, gate voltage with respect to the gate current. So that is the gradient ratio. So it is given as 16 volts per amperes. All right. So from that, IG is given. It is already given there. IG is equal to 500 milliamps means it is 0.5 amperes. So when you substitute, you get VG as 8 volts. I hope you are noting down. If I'm fast, please let me know. Unmute yourself and speak. Okay. So from this, now for this expression, we have got VG. This is our expression. So where ES or EGS, or you can take it as EGS also. So from this, if you substitute EGS, you already know it is given as 15. VG, now you calculated, it is 8. EGS minus, that is 15 minus 8. Divided by IG, you know it is 0.5. Substituting, you will get RS as 14 ohms. Right? I hope you are noting down. Those who have not tried, please note down. Then the second part of the question was calculate gate power dissipation. Okay, given that pulse width is equal to the turn on time and the average gate power dissipation is 0.3 watts. All right, compute the maximum frequency that will be possible when the pulse firing is used. So here what is asked? It is asked find what is the gate power dissipation and the frequency. Okay, so gate power, maximum gate power dissipation, we know the expression Pg is equal to V, a product of V and I, Vg and Ig. So you get 4 watts. So from this expression, I hope you recall this expression where the turn on time is given, Pg average is given, that is, see here, average gate power dissipation is given. Then this maximum power dissipation you have just now calculated. Now what is asked from this expression is the frequency. Calculate the frequency at which the device can be turned on is what asked. So substituting all terms, you will get F as 18.75 kilohertz. This is for those who have not tried. Please go through. If you have any doubt, get it clarified. Please copy this and note down. Okay, now others will be invited. Can I proceed? Okay, now moving on. Let me call somebody to explain this turn-on switching characteristics. Whom shall I call? Raksha Kamath, can you come in?
Yes, ma'am.
So can you see the waveforms there? Is it clearly visible?
Yes, ma'am.
Can you try? Can you try to explain the turn-on switching characteristics?
Okay, ma'am.
What do you understand? What do you see? How do you interpret these waveforms? How do you interpret these waveforms? What information do you get there? Turn-on characteristics, switching characteristics. What are we talking about?
The gate current is increased from 0 to 0.9 of Ig and the hello?
Oh, yeah, I'm listening. Yes.
Yes. At that time, the anode current will be 0. It won't rise. Because anode current is 0, the anode cathode voltage will be at its peak.
Okay.
And the power loss will be minimum, that is from 0, and it rises little bit. And when the gate current has reached Ig, the anode current starts increasing and the anode voltage will start decreasing and the power loss will increase.
Okay. Yeah. Anything else you want to add there? Anything else? Okay, thank you. Shibani, can you come in? Shibani.
Hello, ma'am.
Yeah, you're there? Okay. Can you add points to what was that? I forgot. Yeah. Can you add?
Ma'am, first when you apply the gate voltage at the gate terminal of SCR, there will be gate current, a small rise in the gate current, but then the anode current will be low and then it will increase gradually.
So there are some representations in the waveforms depicted there. So if we have to talk about switching characteristic, then how do you interpret this? How do you interpret this? Any volunteers? Wherein you feel, yes, I know a little bit, I can explain. Anyone like that? Yeah, you have got an opportunity to express yourself. If you feel yes, I can explain to some extent. Can you come in? Try. You need not be perfectly correct. No one is perfect, but you can always try. It just shows how you are able to interpret things with the information what we have already, what we had studied in previous sessions. No one like that from 120 students? 109 are available here. Not even one? Come on, where are everyone? Where are the leaders? Yeah? I want you to speak up. I want you to speak up. It's not that difficult. It's already what we have already discussed. It's not difficult. You can always try. Come on, leaders. Yes. Somebody. Yeah. Come in. I want you to speak. Oh, okay. That means you are inviting me to call you. Fine. Hitesh, come in. Hitesh, come in. You are there?
Yes. Hello, ma'am. Yes, ma'am.
Why were you silent all this time?
Like I couldn't like put everything in the proper words, ma'am.
I told you need not put everything in place, in the right place. You can always try, I said. Can you try now?
Yes, ma'am. Yes, ma'am.
Yes, sure. Good.
So first we apply the gate current to turn on.
Correct.
So as the gate current starts increasing, once it reaches 90% of the gate required gate current to turn on. Hello.
Okay. Yeah, go ahead.
The anode current starts increasing. So it takes around TD time to reach the 10% of the required threshold, IT, that is anode current.
What is TD?
IT, ma'am, IT. It takes TD amount of delay.
What is
Hello.
TD? Is the question. What is TD?
Delay time.
Yeah, delay time. Yeah. Somebody texted you, is it? Okay, good. Go ahead. I know you guys here. Come on.
Okay, ma'am. Then the cathode voltage, it starts. I didn't understand that part of the graph, ma'am, because
Fine. Yeah, thank you for responding and trying. Okay, let me go do it. See here, when we are talking about turn on switching characteristics, if you recall what we had in our previous discussions, switching characteristics means like we are trying to know how the device behaves when it is switching from turn off to turn on condition or turn on to turn off condition. Okay, now here we are discussing turn on condition. Turn on means what? Now the device is turned off. Presently the device is turned off. If we are turning it on, then how does it behave? How are its characteristics? Okay, that is what we are discussing here in this. These waveforms depict or describe us the turn on switching characteristics of an SCR. Okay. Now, by this time, we are aware that if we want to turn on the SCR faster, okay, what do? We give a gate signal. Okay, gate signal is nothing but we apply voltage across gate and cathode terminal, for which there is some current flowing through the gate terminal. Okay, so say this is my gate current. IG is my gate current. That is already applied. Okay. Now to this gate current, how the SCR behaves in its turn on condition is what we are discussing. That is nothing but turn on switching characteristics. All right. Now you have to recall again here. when I said now the device is in turn off condition and I'm turning it on. So when it is in turn off condition, when the device is turned on, the all right, and the current flowing through it will be minimum or zero in ideal case, if you recall that. Okay, so now observe here. Initially, when the device is turned off, the voltage across it will be maximum, all right, and current flowing through it will be minimum or zero. Getting it? Okay. Now observe, as the gate current, as the gate control signal is given, as it is varying. So what happens till it reaches 90% of it? See here, there is no current observed in the device, which means what? There should be sufficient gate current. There should be sufficient gate current where there will be sufficient charge carriers in the device to turn it on. I hope you are getting. You have to recall everything here. You have to visualize the construction. You have to visualize the internal structure there. All right. So there should be sufficient current. Current is nothing but what charge carries, right? So there should be sufficient charges required to multiply the charges and increase the current flowing through the device. All right. So observe here, where does the current starts increasing? After this point, after the 90% of the input or the control signal or the gate current. I hope you're with me. All right. So this is our delay time. So when we are talking about turn on characteristics, if you recall, turn on time is nothing but summation of delay time, rise time, and here it is spread time. Okay. So total turn on period of SCR is nothing but the total time taken with summing up the delay time, rise time, and spread time. So what is delay time? Delay time is nothing but the time required for the anode current to reach to its 10% of its value. Okay, 10% of its maximum value. So this is the delay time. So if you recall internal structure, then what is happening? The charges are getting building up as you are applying the gate current. The charges are slowly building up. Okay, so there is slow increase in the anode current. Okay, so observe the voltage. Now voltage across the device is slowly dropping from its maximum value to its 90% value. Getting it? Okay. And in rise time is the time duration where the anode current reaches from its 10% to 90% of its final value. So again, if you recall the internally, what is happening there internally, now slowly the charge carriers are getting multiplied and they are getting build up inside, so which is nothing but increasing the anode current. I hope you are able to relate the construction, the operation, everything. You have to imagine the two transistors connected back to back. Okay, and internally what is happening there because of the electric field, because of this triggering circuit, control signal, what is internally happening there? Charges are building up, current is flowing, means current is slowly increasing. So you have to relate all basic electronics here. Okay, so if you look at the voltage again in the rise time period, the voltage is dropping from its 90% value to 10% of its value. Okay. Then the spread time is
Cannot hear, ma'am.